In Chem 1A, we learned about the standard enthalpy change for a reaction. Delta H0 RxN. That was the change in enthalpy for a process in which all the reactants and products were in their standard states. And to refresh our memories, the standard states are given here. For a gas, it's the pure gas at 1 atmosphere. For a liquid or solid, it's the pure substance in its most stable form at 1 atmosphere, and the temperature of interest, generally 25 degrees Celsius. For a substance in solution, it's a concentration of 1 mole per liter. Those are defined as the standard states. So the standard entropy change for a reaction, delta S0 RxN, is the change in entropy for a process in which all the reactants and products are in their standard states. Entropy is a state function, just like enthalpy. It doesn't depend on the process. It only depends on the beginning and the ending points, right? So the change in entropy for the reaction is going to equal the entropy of the products minus the entropy of the reactants. But we need to define standard molar entropies. The enthalpies we define as for the elements in their standard states was zero enthalpy. And we had to do that, we had to define zero because you can't calculate absolute values for enthalpy. You can only look at changes. And so we had to pick a point of reference. But for entropy, there is an absolute zero. And this is the third law of thermodynamics. So the entropy of a perfect crystal at absolute zero is zero. So we have a perfect crystal. There are no defects in it. There are no impurities. Everything is perfectly arranged. So W is equal to 1. And the entropy of this is zero because the energy of this is zero. Nothing is moving. At 0 Kelvin, absolute zero, the motion stops. The particles are not even vibrating in place. There's no motion at all. Zero kinetic energy. And so that is zero entropy. Only one possible way to arrange the components. S is equal to K times the natural log of W, and natural log of 1 is 0. Entropy is 0. So entropy is an extensive property, meaning it depends on the amount of substance. If you have a small amount, you have a small amount of entropy. If you have a large quantity of the substance, you have a large amount of entropy. So we look up the standard molar entropy values in a table like this one. So this is in chapter 19. There's another table in the appendix that gives delta H, delta G, and delta S for all kinds of different things. So here we see that none of these are zero, right? Because this is at 298 Kelvin at 25 degrees Celsius. Everything's going to have some entropy. And so here are the amounts per mole of substance. Okay? So at 25 degrees Celsius, the standard entropy of the substance is the energy dispersed into 1 mole of the substance. Depends on the number of places to put the energy. So the number of places is going to be affected by the state of the substance, by its molar mass, by the particular allotrope, by the molecular complexity, and the extent of dissolution. And we'll talk about each of those. So the state. The entropy of a gas is larger than the entropy of a liquid, which is larger than the entropy of a solid. Because gases have more energetically equivalent ways to arrange their components. They have more places to put the energy. So we can compare liquid water and water in the gas state at 25 degrees Celsius, and we see that the entropy for the liquid water is lower than for the gas. The gas is higher. molar mass affects the amount of entropy. If we look at the noble gases, we learned that going down the periodic table, things increase in size. So here we have illustrations of the size of those atoms. And we also know that the molar mass increases, right? If we look at the molar entropy, standard molar entropy, we see that that also increases. So increasing molar mass will give us increased standard molar entropy. The reason for that is a little hard to understand, but the energy states associated with the motion of heavy atoms are more closely spaced, and so that gives more dispersal of energy. The trend only holds if the substances are in the same state. You can't compare like a small gas particle to a large liquid particle. Allotropes. Allotrope just means different forms of the same element. So carbon has more than two, but two allotropes of carbon are diamond and graphite. So both of these are network covalent solids. The atoms are covalently bonded to each other. But in graphite, there are two-dimensional sheets of carbon atoms bonded together, and those sheets are held together by intermolecular forces, whereas in a diamond, the carbon atoms are covalently bonded in a three-dimensional structure. So these atoms have fewer places to put the energy than these, because these can slide and move around a little bit. So graphite is less constrained. It has higher entropy. And molar complexity. Again, comparing within a given state, can't compare liquids to gases. A more complicated molecule is going to have more places to put the energy. Here we're comparing argon and no nitrogen monoxide. Well, the argon is just an atom, right? And it has translational motion in the gas state, but that's pretty much it. No also has translational motion. It can move through space, but it can also rotate. These things can kind of spin, and we can have vibrational motion. That bond can stretch and contract kind of like a little rubber band. And so this has more places to put the energy, so the entropy is greater for NO than AR. Here we're keeping the state the same and the molar mass very close to the same. If we look at CO and C2H4, molar mass is almost identical, but C2H4 has higher higher entropy because it has greater complexity. So carbon dioxide versus C2H4. So this only has the one double bond that could vibrate, stretch, and contract. And now we've got 5 different bonds that could do that. And so this is greater entropy. It has more places to put the energy. If the molar mass and the complexity are both increasing, then the molar entropy will also increase. So here we have. And with 1 oxygen, 2 oxygens, 2 nitrogens, and 4 oxygens, the molar mass is increasing, the entropy is also increasing. Relative dissolution. Dissolving a crystalline solid will increase the entropy, because now we're taking those ions and we're separating them, we're dispersing them into the solution. The energy that was concentrated in the crystal gets dispersed through the solution. So potassium chlorate that's dissolved in water has a higher molar entropy than solid potassium chlorate. So any questions about those? we can calculate the standard, excuse me, we can calculate the standard entropy change for a chemical reaction. And we're going to calculate this in the same way that we calculated standard enthalpy change for a reaction. We're going to subtract the standard entropies of the reactants multiplied by their coefficients from the products. So delta S, this is the final amount of entropy minus the initial amount of entropy. The entropy depends on how much of it is there, and so these are molar enthalpies, and so we multiply by the number of moles. When we did this with enthalpies, some of them were 0, but standard entropies are always non-zero. So let's calculate delta S for this reaction. We have H2S plus 3O2, and it's forming 2H2O and 2SO2. And here are the molar entropies. So delta S for this reaction is going to be, it's products minus reactants. The entropy of the products minus the entropy of the reactants. So the entropy of the products, we have 2 moles of water, and each mole of water is 188.8 joules per mole Kelvin. And we have 2 moles of SO2, so 2 moles times its standard molar entropy. So that's the entropy of the products. This never fits on one line.